when I minimize in L2, which is historically goes back to Gauss, the greatest mathematician of all time. When you minimize something in L2, you do least squares. And you find that the guy that gives you the minimum has a lot of little numbers, a lot of little components, because when you square those little ones, they don't hurt much. But Gauss didn't do least L1 norm. That has different names, basis per suit, and it comes into signal processing and sensing, right? And then it was discovered that if you minimize, as we'll see in that norm, you amazingly get the winning vector is mostly zeros. And the advantage of that is that you can understand what its components are. The one with many small components, you have no interpretation for that answer. But for an answer that just has a few non-zero components, you really see what's happening. And then this is an important one too. Okay, now I'm going to turn just to, so what's the property of a norm? Well, you can see that the norm of C times a vector is just multiplying by 6 or 11 or minus pi or whatever, is the size of C. Norms have that nice property. They're homogeneous or whatever word. If you double the vector, you should double the norm. That double the length, that makes sense. And then the important property is the famous triangle inequality, that if V and W are two sides of a triangle, and you take the norm of V and add to the norm of W, the two sides, you get more than the straight norm along the hypotenuse. Yeah, so those are properties that we require, and the fact that the norm is positive, which is, I won't write down, but it's important too. Okay, so those are norms, and those will apply also to matrix norms. So if I double a matrix, I want to double its norm. And of course, that works for the 2 norm. And actually, probably, so the triangle inequality for this norm is saying that the largest singular value of A plus B, 2 matrices, is less or equal to the largest singular value of A plus the largest singular value of B. And that's, we won't take class time to check minor, straightforward things like that. So now I'm going to continue with the 3 norms that I want to tell you about. That's a very important one. Then there's another norm that's named has an F, and it's named after Frobenius. Sorry about that. And what is that norm? That norm looks at all the entries in the matrix, just like it was a long vector, and squares them all and adds them up. So in a way, it's like the 2 norm for a vector. So the squared, or shall I put square root? Maybe I should. Is the square root of all the little people in the matrix. So A1n squared plus the next A2 squared, and so on. You finally get to AMN squared. You just treat the matrix like a long vector, and take the square root just like so. That's the Frobenius norm, and then finally, not so well known, is something that's more like L1. It's called the nuclear norm. And not all the faculty would know about this nuclear norm. So it is the sum of the sigma of the singular values. I guess there are of them, so that's where we would stop. Oh, okay. So those are 3 norms. Now, why do I pick on those 3 norms? Here's the point, that for those 3 norms, this statement is true. I could cook up other matrix norms for which this wouldn't work. But for these 3 highly important norms, this Eckert-Young statement that the closest rank K approximation is found from the first K pieces, you see that's a good thing, because this is what we compute from the SVD. So now we've solved an approximation problem. We found the best B is AK. And the point is it could use any of those norms. So there would be somebody finally came up with a proof that does all 3 norms at once. In the notes, I do that one separately from Frobenius. And actually, I found in an MIT thesis, I was just reading a course 6 PhD thesis, and the author, who's speaking tomorrow or Friday in IDSS, Dr. Srebro, found a nice new proof of Frobenius, and it's in the notes, as well as an older proof. Okay. You know, as I talk here, I'm not too sure whether it is essential for me to go through the proof either in the L2 norm, which takes half a page in the notes, or in the Frobenius norm, which takes more. I'd rather you see the point. The point is that in these norms, and now what is special about these norms of a matrix? These depend only on the sigmas, only on the, well, I'll finish that sentence because it was true. These norms depend only on the singular values, right? That one at least depends only on the singular value. It's the largest one. This one is the sum of them all. This one comes into the Netflix competition, by the way. This was the right norm to win $1 zillion in the Netflix competition. So what did Netflix put? It did a math competition. It had movie preferences from many, many Netflix subscribers. They gave their ranking to a bunch of movies. But of course, they hadn't seen, none of them had seen all the movies. So the matrix of rankings, where you had the ranker and the matrix, was a very big matrix, but it's got missing entries. If the ranker didn't see the movie, he or she isn't ranking it. So what's the idea about Netflix? So they offered like $1 million prize. And a lot of math and computer science people fought for that prize. And over the years, they got like higher, 92, 93, 94% right. So, but it turned out that this was, well, you had to, in the end, you had to use a little psychology of how people voted. So it was partly about human psychology, but it was also a very large matrix problem with an incomplete matrix. An incomplete matrix. And so it had to be completed. You had to figure out what would the ranker have said about the post if he hadn't seen it, but had ranked, several other movies, like All the President's Men or whatever, given a ranking to those. You have to, and that's a recommender system, of course. That's how you get recommendations from Amazon. They've got a big matrix calculation here, and if you've bought a couple of math books, they're going to tell you about more math books, more than you want to know, right? Yeah. Okay. So anyway, it just turned out that this norm was the right one to minimize. I can't give you all the details of the Netflix competition, but this turned out to be the right norm to do a minimum problem, a best, not least squares. These squares would look at some other norm, but a best nuclear norm completion of the matrix, and now it's so now it's being put to much more serious uses for MRI, magnetic resonance stuff. You know, when you go in and get it's a noisy system, but you get it gives a excellent picture of what's going on. So I'll just write Netflix here. So it gets in the, and then MRIs. So what's the point about MRIs? So if you stay in long enough, you get all the numbers. There isn't missing data. But if you, as with a child, you might want to just have the child in for a few minutes, then that's not enough to get a complete picture, and you have again missing data in your matrix in the image from the MRI. So then, of course, you got to complete that matrix. You have to fill in what would the MRI have seen in those positions where it didn't look long enough. And again, the nuclear norm is the good one for that.